All right, so I'm just going to kind of briefly work through this. Out of all the tests, this is going to be the last one. Kind of bittersweet. So with your de Broglie wavelength, remember that was the ability to predict particles having a wavelength which was very counterintuitive. They understood sound having a wavelength and light having a wavelength. But the idea that particles could have wavelength was very, very counterintuitive. So remember, they've already given you the momentum. So it's just Planck's constant divided by that momentum. On the kinetic energy side, there's a couple of ways you can do this. There's the long way and then there's the short way. So one option is that you take this momentum and you find the velocity, because you know that it's a proton and you know its momentum. Then you divide by the mass. Boom, there's your velocity. You're off to the races. Now, the easier way to do this is to realize that if you solve this for velocity, you get momentum over mass. You substitute that in for velocity, you get p squared over m squared times m over 2. Then it's just momentum squared over 2m. You're still going to have to look up the mass of the proton. This method is a little bit faster because you don't have to find the velocity separately. You do the same math. It's a personal preference thing. Now, the whole key to this next one is that you're going to shoot this thing, and basically what's going to happen is that you're going to have these two nuclei, and at that point of closest approach, all the kinetic energy is going to be changed into ooey. So in that regard, it's like pushing a box and having it slide towards a spring, and that spring compresses, and then all of that kinetic energy would be stored in the spring. So in this situation, all of that energy is stored as ooey. Now, the trick here is, what do you use for your Q values? Well, this is uranium. So you've got 92, so you've got to take 92 times the charge on each proton, 1.6 times 10 to the negative 19th. So that's going to get you one of the Qs, and then the other one is just a proton. So you just use that, boom, there you go. And then you're going to know that kinetic energy, which you found up here. The only thing you're not going to know is R, which is going to be that point of closest approach, what they're calling D. Now, here's the whole key on part D, speaking of D. So this goes out of Einstein's theory of relativity. You have E equals mc squared. M is the mass difference. C is the speed of light. E is how much energy that you've got. So the whole key to this also is this whole idea of binding energy. So the reason that nuclear fission, which is the splitting of a nucleus, works is because of the fact that the masses that you end up with, sorry about the yawn, are a little bit less than what you started with. That's the whole key to this. So this mass here is greater than what you get out of the products. And that's that whole idea of binding energy. So to get the mass difference, you just use E equals mc squared. Hey, you know how much energy is released. You know the speed of light. Solve for the mass. And this is a similar type problem. So calculate the rest energy of the positron. You're just going to use E equals mc squared. Here's the mass of the electron. Remember, positron and electrons are the same thing. The only difference is that a positron has a positive charge and an electron has a negative charge. So you're just going to use E equals mc squared. So basically what this is calculating is that if you could take that electron and turn that thing into pure energy, this is how much energy was going to be released. So now B is a little bit tricky because it determines in electron volts the energy of each emitted photon must have. So technically, this energy that you're going to get, because the proton and positron are going to annihilate each other, technically this answer in terms of pure energy would be twice that. So because the proton and the because the positron and the electron have the exact same mass, when they annihilate each other, then this is how much you're technically going to get twice this energy. But because it asks for the energy in each photon, so basically you take this answer times 2, but then you divide it by 2 again, and so that's why your answers for A and C, or A and B, are the exact same number. Then it calculate the wavelength of the photon. You've got E equals hc over lambda. Solve for lambda. Here's your energy. If you make sure that you are familiar with using this 1240 electron volt nanometers, it's going to make life so much simpler. Okay, you can convert it into joules if you're really hardcore, but it's just a god-awful amount of work. So if you've not embraced that 1240 electron volt nanometers, I highly recommend that you do so. Then the momentum of each photon, and you usually don't think of a photon having momentum, but it does. This is the whole idea of like a light sail that they're going to try and incorporate into like potentially powering spaceships. But basically what you've got is that you're going to calculate the momentum of each photon. Here's Planck's constant. Now, this is technically joule seconds, but joules are Newton meter seconds. So that's why your Newton meters cancel out, and then you're left with Newton seconds, and that's what momentum is measured in. So even though this is joule seconds, when you divide by wavelength, you get Newton seconds, which is what momentum is going to be. Now, but the total momentum is just going to be 0. And here's the reason why. Momentum and energy always have to be conserved. So because of the fact that you've got one photon going in one direction and one photon going in the opposite direction, and because momentum is a scalar quantity, you're going to have like a negative number, and then you're going to have a positive number, and those two are going to add up to 0. Okay, on this one, this was kind of a cool question, mainly because of the fact that they gave you the wavelengths, okay, and then they ask you to calculate this transition. Now, even though they don't specifically ask you about this, these transition states are going to be what's going to happen when you kick electrons out. So this is creating an emission spectrum. If you were to look at the reverse of this in terms of what you would get as being able to absorb this. So if you were to kick this out, remember this thing can, if you were going from the ground state up, then you're going to go from here up to here and from here up to there. That's it. So on an absorption spectrum, you'd only have 2 blank spots because these electrons can only go from here to here to here. Now, as it's returning, it can stop here, and that's where you're going to get that 400 nanometers. But make sure that you understand the difference between those two. So on the way down, you could go from A, and you could start at that stop level and go down to here and then create another transition. But on the way up, you can only go from here up to there, and that's only going to be one step. So anyway, so you got to go through and you've got to calculate the wavelength, the energies associated with this. And again, I'd recommend that 1240 nanometer electron volts. That's going to make life much simpler. So A is just going to be the sum of these two transitions. And then on B, they're going to give you the work function. And remember, that's how much energy it takes to get the free of the electron or that's how much it takes to get Tate out of jail, if you want to think of it that way. So that maximum kinetic energy is going to be K max. Now, if they had asked for stopping energy in volts, that would be that same answer, but only if you're in electron volts. So pay attention to the units on that. De Broglie wavelength, lambda equals h over p. Now, when you look at this in terms of energy, the photons emitted, which one is going to incident on the metal surface, which is just a fancy way that it says that you're going to shine the light on it, which will also result electrons being ejected from the metal. So remember, when you have the photoelectric effect, you have two energies involved. You have the energy of the photon, which is HF, and then you have the energy to overcome the work function. Okay? They're related, but one is the energy of a photon, and one's the energy of electron. You have to keep straight if you're talking about the electron or if you're talking about the photon. So if you do this in terms of this work function of 2.46 electron volts, so this is going to be a situation where to make this happen, you have to overcome that work function. So the only one that's going to have enough energy to do that is that transition to A, because that's the only one with enough energy to make that happen. Okay. Now with this one, this was always odd because they gave these electron volts as negative values, which is kind of odd. Most of the time these are given as positive values, so I don't know exactly why they made these negatives. But anyway, so you can think of it as like being down in an energy well, and n equals 1, when it talks about that principal quantum number, all that's asking is saying, oh, hey, here's n equals 1. That's like the energy level that's closest to the nucleus, and then it goes up from there. So anyway, so it calculates the wavelength associated with each possible transition between the energy levels. So again, make sure on that one you realize you can go from -6 to 3. It can go from -3 to -1, or it could go all the way from -1 down to -6. Now here's what I want you to look at, is that the bigger this transition is, the shorter the wavelength is going to be. So if you notice, what would happen here is that you're going to only kick out 3 distinct bands of light, because these and this is the bigger idea. These electrons can only exist at certain energy levels, and since they can only exist at certain energy levels, this is why you only get, 3 distinct bands of light that would come out of this deal. Pay attention to D. They want this energy in joules, and on this one, I'm not going to expect you to know this on the test, but just kind of a random thing if you ever want to keep anything in mind. The visible spectrum of light is from 380 to 740 nanometers. Don't memorize that for the test. But here's what you should know, is that 740 nanometers is going to be red light, because that's on the longer wavelength, and that 380 is going to be your violet light. And I tried to write in violet, and that didn't work out. Anyway. So here's the last one. You've got this shining on. Here's the metal surface. This maximum kinetic energy, notice that this is in joules. So, and K max is HC minus your work function. So basically what we're saying is that Tate has been freed, and he has been freed with this amount. So you know the 400 nanometers, so that allows you to calculate how much energy Liza has brought with her. So this tells you how much money Liza has. This tells you how much money they have left over, and so what you're trying to find is how much did it cost Liza to get Tate out of jail. Okay? So once you get that, then you're calculating that work function, which is what that is how much it costs to get Tate out of jail. Your stopping potential, and stopping potentials, remember, are that has to be in volts. So the easiest thing to do with this is that you can calculate that in like electron volts, which is that energy per electron. And then the last thing is going to be the momentum, and you could use p squared over 2m and solve for p, or you can use kinetic energy equals 1/2 mv squared, find the velocity and put that into momentum. Doesn't make any difference. Okay, kids, that's it. Like I said, it's bittersweet, and I'd work through these problems, especially on the photoelectric effect, know the difference between the energy of the photon and the energy of the electron, and not to be confused with the energy of a crouton, which is something completely different. So anyway, kids, hopefully this helps you get ready for the test tomorrow. I'd go back through and work all that. If you have not read the chapters, I highly recommend that you kind of read the chapters and kind of see what's going on with that. So anyway, that's it. And we are all professionals, and you know what you must do.